June 20th, 1944. Aboard the crippled carrier Zuikaku, Vice Admiral Jisaburo Ozawa stared at the decimation report with hands that wouldn't stop shaking. In 2 days of combat, the mobile fleet had lost 480 aircraft. Not damaged, not missing, destroyed. The Americans had lost 123, most to fuel exhaustion, not combat. The ratio was catastrophic, but what paralyzed Ozawa wasn't the numbers on the page. It was what he had witnessed through his binoculars. Wave after wave of Japanese aircraft, flown by pilots with barely 40 hours of training, intercepted not by dozens but by hundreds of American fighters. Grumman F-6F Hellcats, they appeared in formations so vast they darkened the sky. Blue-grey machines that climbed faster, dove harder, and absorbed punishment that would have shredded a Zero. His radio operators had recorded American pilots joking over open frequencies, calling the battle a turkey shoot. Discussing the engagement like target practice, Admiral Chuichi Nagumo, who had commanded the Pearl Harbor strike force, sat in silent devastation in his headquarters bunker on Saipan. Through 3 years of war, he had watched American air power transform from a nuisance into an avalanche, the mathematics of annihilation. The interrogation rooms of post-war Tokyo would reveal that Japanese naval leadership had possessed accurate intelligence about American aircraft production. They had simply refused to believe it was possible. Captain Toshikazu Omai, operations officer for the combined fleet, documented in testimony to the U.S. Strategic Bombing Survey. His reaction upon seeing production figures: "We estimated Grumman was building perhaps 200 Hellcats per month. Our intelligence indicated they were producing 1 aircraft every hour, around the clock. We dismissed this as propaganda. It was not propaganda. Grumman Aircraft Engineering Corporation, operating from a single plant at Bethpage, Long Island, produced 12,275 F-6F Hellcats during the war. 11,000 of those aircraft rolled off the assembly lines in just 24 months. At peak production, a complete Hellcat emerged from the factory every 60 minutes. 24 aircraft per day, 700 per month. Japan's entire aviation industry, comprising dozens of companies across the home islands, produced 76,320 military aircraft during the entire war. America produced 324,750. The ratio, 4.3 to 1. But numbers alone didn't explain the catastrophe unfolding in Philippine waters. The Hellcat revelation. When America mass-produced excellence, December 4th, 1943. The Kwajalein area. The first large-scale air battle involving the F-6F Hellcat, 91 Hellcats engaged 50 Mitsubishi, a 6 M0s, once Japan's most feared fighter. The Americans shot down 28 Japanese aircraft. They lost 2 Hellcats. Japanese pilots returning from the engagement filed reports that were initially dismissed as hysteria. The new American fighter was faster than the Zero. It could absorb multiple 20mm cannon hits and continue fighting. It could outclimb anything in Japanese inventory. When it dove, nothing could follow. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Commander Minoru Genda, architect of the Pearl Harbor attack, received these reports with growing alarm. He ordered technical intelligence teams to examine every scrap of wreckage from downed Hellcats. What they discovered shattered assumptions about American industrial capability. The Pratt & Whitney R 2800 double Wasp engine produced 2,000 horsepower. Japanese fighters used engines producing 1,100 horsepower. The Hellcat carried 6 50-caliber machine guns. A 2-second burst unleashed 130 rounds. The lightly built Zero could not absorb that firepower. Most revealing, every Hellcat part was machined to precise tolerances. Components were completely interchangeable between aircraft. American ground crews could swap engines in 30 minutes using pneumatic tools. Japanese crews required 3 days, hand-fitting parts individually. The pilot catastrophe. Training hours versus training minutes. Admiral Ozawa's greatest shock during the Philippine Sea battle wasn't the Hellcats' performance, it was who was flying them. Post-war interrogations revealed Japanese intelligence had tracked the age and experience of captured American pilots. Average age, 21 years old. 5 hours. Average time in combat aircraft, 250 hours. Japanese replacement pilots arriving at forward bases in mid-1944 averaged 40 hours total flight time. 40 hours, many had never landed on a carrier. Some had never fired their guns. American pilots were practicing gunnery with more ammunition than Japan allocated for combat operations. The training differential created a death spiral. When war began in 1941, Japanese Navy pilots averaged 700 hours flight time. By January 1945, this had dropped to 275 hours. Army pilots fell from 500 hours to 130 hours. The Americans moved in the opposite direction. In 1943, the U.S. Navy increased training requirements to 500 hours. By 1944, this reached 525 hours. Commander Masatake Okumiya, survivor of both Midway and the Philippine Sea, testified about the psychological impact of American training superiority. "We sent children against veteran warriors. Our pilots knew they were inadequately trained. They climbed into their cockpits knowing they would die. Not might die, would die. American pilots climbed into superior aircraft knowing they would probably return." The industrial multiplication factor. Japan trained 46,000 pilots during the entire war. America trained 250,000. But the disparity was greater than a 5-to-1 ratio suggested. America rotated experienced pilots out of combat into training roles. Veterans taught the next generation. Japan kept experienced pilots in combat until they were killed. When they died, their knowledge died with them. The legendary Japanese ace Saburo Sakai wrote in his memoirs about the training regime of 1938. More than 1,500 applicants, 70 selected, 25 graduated. By 1944, Japan was accepting anyone who could walk and had 20/20 vision. The fuel equation made training impossible. Japanese pilots practiced with gliders during the first month of training to conserve aviation gasoline. American training consumed more fuel than Japanese combat operations. The U.S. Navy used fuel for practice that exceeded Japan's entire monthly allocation. June 19, 1944. The Great Marianas Turkey Shoot. The day began at 5:15 a.m. when American radar detected the first Japanese strike wave. Before the Japanese aircraft came within visual range, 450 Hellcats were airborne. Task Force 58, commanded by Vice Admiral Mark Mitcher, had launched the largest fighter screen in naval history. 15 American carriers, each carrying up to 30 Hellcats. The Japanese had planned to launch a coordinated strike beyond the range of American fighters, land on Marianas airfields to refuel, then attack the American fleet from behind. It was tactically sound. It was also based on calculations that were 3 years out of date. American carriers now operated Hellcats, with combat ranges exceeding 1,000 miles. The Japanese hammer and anvil would catch only American fighters at both ends. What followed was not a battle. It was a massacre. Japanese aircraft, many flown by pilots who had never seen combat, encountered defensive formations they had no chance of penetrating. Lieutenant Alexander Vratsiu, flying from USS Lexington, shot down 6 Japanese aircraft in 8 minutes. Lieutenant William Hardy earned his ace status in a single sortie, destroying 5 aircraft in 70 minutes. These weren't exceptional engagements. They were routine. American pilots described Japanese aircraft as hanging in the air, flying so slowly, so predictably, that veteran Hellcat pilots had to deliberately slow down to avoid overshooting their targets. The final tally? Day 1 saw 346 Japanese carrier aircraft destroyed. Over 2 days, combined air and sea combat eliminated 480 Japanese aircraft. The Americans lost 23 aircraft to enemy action on June 19th. 23. The kill ratio was 19-1. But even this staggering figure understated the catastrophe. Japan had committed nearly every carrier-qualified pilot remaining in its inventory. Most died. Training replacements would require months Japan didn't have. The submarine scissors. Precision cutting of carrier aviation. While Hellcats filled the sky, American submarines demonstrated another dimension of industrial superiority. USS Albacore torpedoed the carrier Taiho with a single shot. The carrier's aviation fuel system, poorly designed and maintained, created vapor clouds that ignited hours later. The explosion destroyed the fleet's flagship. USS Kavala struck the carrier Shokaku with 3 torpedoes. The veteran carrier, survivor of Pearl Harbor, Coral Sea, and Santa Cruz, broke apart and sank. In minutes, 2 fleet carriers, Japan, irreplaceable resources, Japan, vanished. The submarines that killed them represented depth of industrial capacity Japan couldn't imagine. America commissioned 228 submarines during the war. Japan built 126. But the technological gap exceeded numbers. American submarines used radar, advanced torpedoes, and damage control systems that allowed them to survive depth charging that would have sunk Japanese boats. Most importantly, America had submarines to spare for training, for experimental tactics, for replacement of losses. Japan used submarines as cargo vessels. Desperate to resupply isolated garrisons, valuable submarines hauled rice instead of hunting enemy shipping. This single fact, IA's submarines reduced to cargo delivery, epitomized the resource catastrophe. The Bethpage assembly line, manufacturing air supremacy, Grumman's plant. Number 3 at Bethpage employed 25,000 workers at peak production. Women comprised 40% of the workforce. They operated pneumatic riveters, electrical welders, and precision machine tools. The factory operated 24 hours per day, 3 shifts, 7 days per week. A single American factory employed workers numbering 71% of Japan's entire aircraft industry workforce of 35,000. The assembly line used techniques Japan couldn't replicate. Prefabricated sections built in factories across Long Island were transported to Bethpage for final assembly. Electric welding replaced riveting for major components. Engines arrived from Pratt & Whitney already tested and certified. Japanese aircraft manufacturing remained artisanal. Master craftsmen hand-fitted parts. Engines required individual adjustment. Quality control depended on inspectors' experience, not measured tolerances. Mitsubishi required 3 weeks to build a twin-engine bomber. Grumman completed a fighter in days. The replacement revelation, when victory became mathematically impossible. Admiral Ozawa's diary entry from June 22, 1944, revealed the moment Japanese naval aviation died. Lost 3 carriers, 480 aircraft, perhaps 400 pilots. Americans will replace their losses in weeks. We cannot replace ours in years. The war is lost. He was correct. Within 6 months, American carrier air groups returned to full strength. Replacement Hellcats arrived by the dozen. Pilots with 500-plus hours training filled empty cockpits. Japan never recovered from the Philippine Sea losses. The mathematical reality was absolute. Essex-class carriers entered service throughout 1943 to 1944. 17 were commissioned, each designed to operate 90 aircraft. Independence-class light carriers added 9 more ships. By war's end, America possessed 141 carriers of all types. Japan completed 3 additional fleet carriers during the entire war. 3. The disparity was 4-7 to 1 inch America's favor. When Japan lost a carrier, the fleet permanently contracted. When America lost a carrier, 2 more appeared within months. The night of endless Hellcats. Psychological destruction. American dominance extended beyond daylight hours. F-6 F-5 Newton's night fighters, equipped with radar, hunted Japanese aircraft in darkness. More than 1,400 Hellcat night fighters entered service. They carried AI radar that detected targets 5 miles away. Japanese pilots, already overwhelmed by day combat, now faced interception at night. Pilots returning from missions reported being tracked by unseen enemies. Radio operators heard American pilots coordinating attacks on targets the Japanese couldn't see. The psychological impact exceeded material losses. When the sky belonged to the enemy 24 hours per day, when every mission might end in flames without ever seeing the attacker, morale collapsed. Survivors described the American Combat Air Patrol as the Big Blue Blanket, an omnipresent shield that covered the fleet at all times. This constant Hellcat presence represented industrial capacity Japan simply didn't possess. Keeping 450 fighters airborne simultaneously required vast numbers of aircraft, pilots, fuel, ammunition, and maintenance personnel. Japan couldn't sustain 450 fighters across its entire Pacific theater. America maintained that force over a single invasion fleet. The final admission, Ozawa's post-war testimony. Vice Admiral Ozawa's interrogation by U.S. Strategic Bombing Survey officers produced the most comprehensive admission of technological defeat in naval history. His testimony, delivered in precise detail, documented every aspect of Japan's failure. The Hellcat shocked us, not because of a single characteristic, but because of everything simultaneously. It was fast, heavily armed, strongly built, and flown by well-trained pilots. Our intelligence had warned us about superior American industry. We didn't understand what this meant in practice. One American factory produced more fighters per month than our entire nation. Their pilots trained longer, flew better aircraft, and faced little danger. Ours trained briefly, flew inferior machines, and died immediately. The mathematical outcome was never in doubt. We discussed spirit overcoming material disadvantage. Spirit cannot defeat industrial capacity of that magnitude. Commander Okumiya's testimony added technical specificity. We examined crashed Hellcats whenever possible. The engine was marvels of engineering. The hydraulics, electronics, fuel systems, every component represented manufacturing capability we couldn't approach. A single Hellcat contained more advanced technology than our newest fighters. Most devastating was learning that Hellcats were considered obsolescent by American standards when they entered service. They were building even better fighters simultaneously. We were struggling to match American weapons of 1,943, while they prepared weapons of 1,945. The cumulative destruction, numbers that ended naval aviation. Post-war analysis revealed the quantitative impossibility of Japanese victory in the air. The statistics formed an equation with only one solution: carrier aircraft production, USA 140, et un carrier, Japan 17 carriers, 8,3 tonnes. Fighter production specifically for carriers, F-6F Hellcat alone, 12,275 units. All Japanese carrier fighters combined during the war, approximately 15,000 units. But Japan also needed fighters for land bases, leaving perhaps 8,000 for carrier operations. The Hellcat, a single American fighter type, nearly equaled Japan's total carrier fighter production. Total military aircraft, USA 324,750, Japan 76,324, 0.3 to 1. But breaking down by roles revealed worse disparities. Carrier-capable aircraft, USA possessed surplus capacity. Japan struggled to meet minimum requirements. Pilot training hours. Average American pilot, 1,944, 525 hours. Average Japanese pilot, 1,944, 40 to 275 hours depending on service branch. Training ratio, 2 to 1 at minimum, 1:3 to 1 at peak. Combat. Effectiveness. The 1:9 to 1 kill ratio at Philippine Sea represented the accumulated effects of superior training, superior aircraft, superior tactics, and industrial depth. The Turkey Shoot wasn't one battle. It was the culmination of 3 years of American industrial mobilization, creating a force Japan couldn't resist. The August occupation, when the factory came to visit, September 2nd, 1945, Tokyo Bay. The surrender ceremony aboard USS Missouri represented the final humiliation for Japanese naval aviation. Admiral Ozawa stood on shore, watching the carrier fleet at anchor. More than 100 carriers visible in a single harbor, each carrying more aircraft than Japan had possessed at Midway. American ground crews serviced Hellcats on carrier decks. Maintenance that would have required days for Japanese mechanics took American crews hours. Replacement parts arrived by the ton. Entire engines swapped in minutes. The industrial capacity gap, theoretical in 1942, was now physically present in Japan's most important harbor. Within weeks, occupation forces established air superiority over Japan using forces considered surplus by American standards. Hellcats patrolled Japanese skies as demonstration units. The message was clear. These were the fighters that destroyed your air force. We have thousands more. We can build thousands more. Resistance is mathematical impossibility. The pilot testimony. When warriors met factories. Interviews with surviving Japanese naval aviators revealed the psychological impact of facing industrial supremacy. Lieutenant Zenji Abe, who survived multiple encounters with Hellcats, described the moment he understood Japan had lost. My third mission over Saipan. We launched 16 fighters, met perhaps 50 Hellcats. I survived only because American pilot chasing me was called away to intercept bombers. As I fled, I saw formations of Hellcats climbing to altitude. Not dozens, hundreds. The sky was blue-grey with American fighters. I returned to my carrier and reported to my commander. Told him Americans had unlimited aircraft. He ordered me to report to medical officer for evaluation. Thought I was suffering combat fatigue. But 2 days later, everyone saw the same thing. That's when we knew. You cannot defeat an enemy who manufactures fighters faster than you can shoot them down. Commander Tadashi Nakajima documented his squadron's encounters with Hellcats in personal letters later recovered. June 19th. Intercepted American bombers. Engaged by 30 Hellcats. Lost 4 pilots. Killed 2 Americans. Moral victory, we claimed. June 20th. Engaged by 40 Hellcats. Lost 6 pilots. Killed 1 American. June 21st. Cannot launch. No pilots remain with carrier qualification. Squadron effectively destroyed in 3 days. The logistical multiplication. Hellcats that never stopped coming. The true measure of American industrial supremacy wasn't production numbers, it was sustainability. Japan struggled to maintain frontline aircraft. Engine overhauls required weeks. Replacement parts didn't exist. Battle damage often meant permanent loss, even for repairable aircraft. America maintained Hellcats effortlessly. Damaged fighters returned to carriers. New engines arrived within hours. Airframe damage was patched with prefabricated sections. Aircraft that would have been written off as total losses in Japanese service were returned to combat status in days. Grumman manufactured not just fighters, but an entire logistical system. Spare parts inventory, maintenance manuals, specialized tools, trained mechanics, etc. The industrial infrastructure supporting Hellcats exceeded Japan's capacity to build aircraft in the first place. The F-6F was an engineered product designed for mass production and field maintenance. Japanese fighters remained craftsman-built machines requiring artisan care. When skilled mechanics died, maintenance quality collapsed. When supply lines were cut, aircraft couldn't be repaired. By 1944, Japan had aircraft that couldn't fly due to lack of spare parts, fuel, or trained personnel to service them. The final statistical verdict, 1-9-1. The Hellcats combat record stands as history's most comprehensive demonstration of industrial capacity determining military outcomes. Final tallies. 5,156 enemy aircraft destroyed by Hellcats. 270 Hellcats lost in air-to-air combat. Kill ratio, 19.1-1. But these numbers represented only aerial victories. Hellcats also performed ground attack missions, launching 60,000 rockets against land targets and enemy shipping. They flew fighter-bomber missions, carrying 2,000 pounds of ordnance. They operated as night fighters. They performed reconnaissance. The Hellcat was a weapons system, not merely a fighter. 307 American pilots became aces, flying Hellcats, meaning they scored 5 or more aerial victories. Commander David McCampbell achieved 34 victories, all in Hellcats. The aircraft created aces through combination of performance, reliability, and availability. Japanese pilots achieving ace status became increasingly rare as the war progressed, not due to lack of skill, but lack of survival. Epilogue. The admission that changed everything. The testimony of Japanese admirals about the F-6F Hellcat represented more than military analysis. It was recognition that modern warfare had become industrial competition disguised as combat. When Admiral Ozawa stated, "We fought the ocean itself," he meant America's capacity to produce Hellcats exceeded Japan's capacity to destroy them. The lessons resonated through Japanese post-war reconstruction. Industrial capacity, quality control, mass production, trained workforce, AA, the elements that built 12,275 Hellcats, became the foundation of Japan's economic miracle. Companies like Toyota and Sony applied American manufacturing principles learned through defeat, but the human cost remained. 40,000 Japanese pilots died during the war, many of them in their first or second combat missions, flying obsolete aircraft against opponents they had no training to defeat. They were brave, they were determined, they were sent to die by leadership that believed spirit could overcome factories. The Hellcat didn't just win air superiority, it demonstrated that in industrial warfare, the nation that can mass-produce excellence inevitably defeats the nation that can only handcraft adequacy. Grumman built 1 Hellcat per hour. That simple fact decided the Pacific Air War more than any tactic, any strategy, any sacrifice. When 500 Hellcats filled the sky over the Philippine Sea on June 19, 1944, they represented not just American air power, they represented the assembly lines of Bethpage, the pilot training schools across America, the fuel refineries of Texas, the steel mills of Pennsylvania. They represented industrial capacity Japan couldn't match, couldn't overcome, couldn't survive. Admiral Ozawa was right. They never stood a chance. But in understanding why, in documenting precisely how American industry achieved victory, Japanese leadership created knowledge that would transform defeat into future prosperity. The Hellcat won the war. The lessons it taught built the peace. The waterproofing revolution that began with Staff Sergeant Henderson's improvisation expanded exponentially through March 1945. What started as individual mechanics solving immediate problems became systematic transformation of American logistics capabilities. The story of how this innovation spread reveals principles about military adaptation that German High Command never comprehended. March 12, 1945, 3rd Army Headquarters, Luxembourg. Lieutenant General George S. Patton reviewed after-action reports from 1st Army's Rhine crossing operations. The reports mentioned almost casually that supply vehicles had crossed multiple rivers without bridging equipment. Patton, whose aggressive tactics consistently outpaced his supply lines, immediately grasped implications. He summoned Colonel John Conklin, 3rd Army's chief engineer. Patton's question was characteristically direct. "Can we do what 1st Army's doing? Cross rivers without waiting for your bridge builders?" Conklin, who had already been investigating the waterproofing techniques through informal channels, responded affirmatively. "Sir, we can have every vehicle in 3rd Army watercrossing capable within 10 days. Patton's authorization was equally direct. "Make it happen. I don't care about regulations. I care about speed." Within 48 hours, 3rd Army mechanics were waterproofing vehicles using techniques learned from their 1st Army counterparts. The knowledge transfer happened entirely through sergeant-to-sergeant communication. No official technical manuals existed. No headquarters staff coordinated the effort. Mechanics simply shared solutions that worked. By March 20th, 3rd Army possessed watercrossing capability across thousands of vehicles. Patton's subsequent advance through southern Germany exploited this capability ruthlessly. His forces crossed the main river at 17 separate locations simultaneously, overwhelming German defenders who expected attacks at bridges only. German defensive doctrine, which concentrated forces at bridges and fords, became obsolete instantly when attackers crossed rivers everywhere. The tactical flexibility provided by waterproofed vehicles transformed operational planning. Before waterproofing, army movements were constrained by bridge locations. Advance routes were predictable. Germans defended bridges, knowing Americans required them. After waterproofing, American forces moved independently of bridges. Advance routes became unpredictable. German defenders couldn't concentrate forces because attacks came from unexpected directions. 7th Army, operating in southern sectors, adopted waterproofing even more aggressively. General Alexander Patch, commanding 7th Army, authorized battlefield modifications that extended beyond jeeps. His engineers waterproofed 2.5-ton trucks, enabling heavy supply transport through rivers. The modifications required more extensive work than jeep waterproofing but used identical principles. Cover electrical systems, elevate air intakes, seal vulnerable components. By late March, 7th Army was moving supply columns through rivers that Germans considered impassable to heavy vehicles. The German 19th Army, defending the Upper Rhine, reported with disbelief that American trucks were fording the Rhine's tributaries carrying full loads. Wehrmacht intelligence analysts dismissed these reports initially. Preparing and narrating this story took us a lot of time, so if you are enjoying it, like this video, it means a lot to us. Now back to the story. Their calculations proved decisively that loaded trucks couldn't ford rivers exceeding 2 feet depth. The reports must reflect exaggeration or misidentification, but field commanders knew what they observed. American supply trucks were crossing rivers that engineering manuals declared impossible. The reports were accurate. The engineering manuals measured capability by limitations that Americans had overcome through improvisation. The waterproofing innovation's spread demonstrates how decentralized initiative multiplies force effectiveness. No central authority directed the adaptation. No official program coordinated implementation. Individual soldiers recognized useful techniques and adopted them. Sergeants trained sergeants. Mechanics helped mechanics. The entire transformation happened through lateral communication networks that German military structure couldn't replicate. German military organization emphasized vertical command structures. Information flowed upward to headquarters. Decisions flowed downward to units. This system produced excellent coordination when doctrine applied, but it prevented lateral knowledge transfer. A sergeant in one unit who solved problems couldn't share solutions with sergeants in other units without official channels approving the transfer. American military culture, though hierarchical officially, functioned informally through horizontal networks. Sergeants from different units communicated freely. Mechanics shared techniques without awaiting authorization. Solutions spread organically through personal relationships rather than official channels. This cultural difference, subtle in peacetime, proved decisive in warfare where adaptation determined survival. The strategic impact of waterproofed vehicles extended beyond tactical flexibility. German defensive planning for the entire Western Front assumed rivers created barriers requiring bridging operations. Wehrmacht strategists positioned forces to defend river lines, concentrating at bridges and known fords. This deployment made perfect military sense when rivers actually functioned as barriers. But when American vehicles crossed rivers everywhere, German defensive deployments became counterproductive. Forces concentrated at bridges defended positions Americans bypassed. Units positioned at fords watched Americans cross upstream and downstream simultaneously. The entire German defensive strategy collapsed because its fundamental assumption that rivers channeled movement was obsolete. Field Marshal Walther Model, commanding Army Group B, recognized this reality explicitly. His final orders to subordinate commanders acknowledged that defensive positions based on river lines are no longer viable against enemies who cross rivers without bridges. model statement, written days before his suicide, represented professional recognition that conventional defensive warfare had become impossible. The technological simplicity of waterproofing makes its impact more remarkable. No scientific breakthrough enabled river crossings. No industrial miracle produced specialized equipment. Canvas, rubber seals, and pipe fittings materials available at any supply depot provided everything necessary. The innovation required no resources beyond what every army possessed. What separated American from German forces wasn't material but mindset. American sergeants saw problems and solved them. German sergeants saw problems and awaited orders. This difference determined campaign outcomes more decisively than weapon superiority or tactical doctrine. American forces that improvised solutions defeated German forces that followed procedures exactly, even when German procedures were technically superior. The expansion of waterproofing capabilities continued through April 1945. By month's end, American forces in Europe possessed comprehensive watercrossing capability across virtually all vehicle types. Ambulances were waterproofed, enabling casualty evacuation through rivers. Command vehicles crossed water, maintaining communications regardless of bridge status. Artillery prime movers forded rivers, deploying guns at unexpected locations. The cumulative effect transformed warfare fundamentally. Armies that could cross rivers anywhere possessed mobility advantages that nullified defensive preparations. German forces, trained for methodical defense of prepared positions, faced enemies who simply bypassed prepared positions entirely. Defensive warfare became exercises in futility when attackers ignored the obstacles defenses were designed to exploit. The psychological impact on German forces was devastating. Soldiers trained to defend river lines watched enemies cross rivers casually at locations doctrine declared impassable. The experience undermined confidence in military judgment. If basic assumptions about rivers as barriers were wrong, what other doctrinal certainties might be false? German combat effectiveness degraded not merely from material inferiority, but from recognition that their military science was obsolete. American forces demonstrated repeatedly that improvisation defeated doctrine. This realization, perhaps more than battlefield defeats, convinced German soldiers that continued resistance was pointless. Why fight for positions that enemies could bypass effortlessly? Post-war interviews with German officers revealed consistent themes. They acknowledged American material superiority, but emphasized more strongly American adaptability. General Oberst Alfred Jodl testified, "We planned defenses assuming rivers created barriers. Americans simply drove through rivers as if barriers didn't exist." This capability, more than any weapon system, made defensive warfare impossible. Field Marshal Albert Kesselring stated explicitly, "American logistics succeeded because supply vehicles operated independently of infrastructure. We destroyed bridges systematically, achieving nothing because Americans required no bridges. This independence from conventional infrastructure requirements proved militarily insurmountable." The lessons from waterproofed jeeps extend beyond World War II specifics. Organizations that empower individuals to solve problems adapt faster than organizations that require official authorization. Innovation emerges from necessity when people have freedom to experiment. Standardized solutions often prove less effective than improvised adaptations for specific situations. American military effectiveness in 1945 resulted fundamentally from cultural characteristics that encouraged initiative. Soldiers who identified problems were empowered to develop solutions. Officers who supported unauthorized modifications prioritized results over procedure. This pragmatism, which seemed undisciplined to German observers, produced tactical advantages no amount of planning could replicate. The contrast between Staff Sergeant Henderson, improvising waterproofing, and German mechanics awaiting official equipment modifications exemplifies cultural differences that determined war's outcome. Henderson saw a problem, developed a solution, and implemented it immediately. German mechanics identified identical problems, reported them through channels, and waited for authorized solutions that never came. Both systems had logic. Henderson's approach risked inconsistent results and unauthorized modifications. German procedure ensured standardization and official approval. But in warfare where adaptation determined survival, Henderson's improvisation proved vastly superior to German standardization. Speed of implementation mattered more than procedural correctness. The waterproofing innovation's rapid spread through American forces demonstrated another crucial principle. Informal networks transfer knowledge faster than official channels. Henderson's technique reached thousands of mechanics in weeks through personal communication. Official technical manuals, by contrast, required months to develop, approve, and distribute. By the time official documentation existed, the innovation had already spread through informal channels and evolved through practical application. German military culture, which valued formal documentation and official authorization, couldn't replicate this rapid knowledge transfer. Innovations had to be documented officially, approved through channels, and distributed formally. This process, which ensured standardization and accountability, also ensured that innovations reached field units months after immediate need had passed. The final weeks of warfare in Europe demonstrated waterproofed vehicles' enduring impact. As German resistance collapsed, American forces advanced with unprecedented speed. Supply lines maintained pace with combat units, despite systematic destruction of bridges and infrastructure. The advance succeeded partly through German demoralization, but decisively through logistics that functioned despite obstacles. The strategic lesson remained clear: armies that adapt to conditions defeat armies that await ideal conditions. American forces that improvised solutions maintained operational tempo regardless of obstacles. German forces that followed doctrine exactly found that doctrine no longer applied to circumstances they faced. This flexibility, more than material superiority, determined the war's final campaign. Staff Sergeant William Henderson returned to civilian life in Ohio, working as a mechanic at a Chevrolet dealership. He rarely discussed his wartime service. The waterproofing modifications that changed warfare seemed, to him, merely obvious solutions to practical problems. His perspective exemplified the mindset that made American military adaptation possible. Problems existed to be solved, rather than obstacles to halt progress. Major William Carter, who authorized the unauthorized modifications, continued his engineering career in the Army Corps of Engineers. He later stated that his Remagen decision to implement waterproofing without official approval represented the most consequential choice of his military career. His willingness to violate procedure for tactical advantage exemplified leadership that prioritized mission success over regulatory compliance. The legacy of waterproofed jeeps, crossing 5 rivers in one night, extends beyond tactical victory. It demonstrates that determined individuals solving practical problems overcome obstacles that seem insurmountable to rigid thinking. When necessity empowers adaptation, impossible becomes routine. The principle remains valid today. Organizations that encourage initiative defeat those that demand compliance. Victory belongs to those who adapt, not those who await authorization. The technical evolution of waterproofing modifications through March and April 1945 reveals systematic refinement that transformed crude improvisation into sophisticated methodology. What began as Staff Sergeant Henderson's canvas and rubber solution evolved into comprehensive protocols that addressed challenges Henderson never encountered. This evolution demonstrates how practical experience generates knowledge that theoretical engineering cannot anticipate. March 15, 1945, 291st Engineer Combat Battalion Maintenance Depot, east of Remagen. Sergeant First Class Robert Mitchell documented waterproofing failures from the previous week's operations. Of 127 vehicles that attempted river crossings, 11 experienced engine failures. Mitchell's analysis identified patterns. Failures occurred predominantly in vehicles crossing rivers with strong currents. Water infiltration happened not through engine compartments, which were adequately sealed, but through transmission and differential housings. The original waterproofing focused on engine protection because engines were obvious vulnerability points, but extended submersion exposed secondary vulnerabilities. Transmissions, designed to vent heat during operation, possessed breather holes that admitted water under pressure. Differentials, similarly vented, flooded when submerged. The water contaminated lubricants, causing mechanical failures hours after successful crossings. Mitchell's solution required understanding not just engines but complete drivetrain systems. He developed secondary sealing protocols using rubber tubing extended above water level, creating breathing systems that maintained pressure equalization without water infiltration. The modification added approximately 90 minutes to waterproofing procedures, but reduced failure rates to less than 2%. Mitchell's refinement spread through the same informal networks that distributed original waterproofing techniques. By late March, mechanics across multiple armies were implementing enhanced sealing protocols. No official directive mandated the changes. No technical bulletin documented the procedures. Mechanics simply recognized superior solutions and adopted them. This organic evolution of technique exemplified American military culture's strength. German military development, by contrast, required formal testing and official authorization before implementing modifications. When Wehrmacht engineers identified similar drivetrain vulnerabilities in specialized amphibious vehicles, they initiated proper engineering studies. These studies, conducted at testing facilities in Germany, produced technically superior solutions, but the solutions reached field units 6 months after identification of problems. American mechanics, working with available materials at forward maintenance depots, solved identical problems in days. Their solutions were less elegant technically, but immediately applicable operationally. Speed of implementation trumped technical sophistication. The comparison reveals fundamental truth about military effectiveness. Adequate solutions implemented immediately defeat perfect solutions implemented eventually. The waterproofing evolution addressed progressively complex challenges. Initial modifications enabled fording rivers up to 3 feet deep. Subsequent refinements extended capability to 4 feet. By April 1945, experienced mechanics were preparing vehicles for 5-foot fording operations. Each capability expansion required solving additional problems. Deeper water required higher air intakes. Mechanics fabricated extended snorkels using exhaust pipes, steel tubing, and improvised brackets. These additions, technically unauthorized modifications to standard vehicles, became standard practice across engineering battalions. The modifications were crude by engineering standards, welded joints, improvised clamps, non-standardized components but functionally effective. German observers, examining captured American vehicles, noted the crude nature of modifications with professional disdain. Wehrmacht technical reports described American waterproofing as improvised field modifications lacking proper engineering standards. The assessment was technically accurate but strategically irrelevant. Crude modifications that enabled river crossings proved vastly more valuable than proper engineering that never reached implementation. The operational expansion of waterproofing capability extended beyond combat vehicles. By mid-April, American forces were waterproofing support vehicles including ambulances, communications trucks, and mobile workshops. Each vehicle type presented unique challenges requiring specific solutions. Ambulances required patient compartment waterproofing to protect wounded soldiers during crossings. Communications trucks needed electronic equipment protection beyond standard waterproofing requirements. Technical Service Company, 82nd Airborne Division, developed specialized protocols for communications vehicle waterproofing. Radio equipment required not just water exclusion but moisture control to prevent condensation damage. Technicians created sealed compartments using canvas and rubber, incorporating desiccant materials to control humidity. The modifications were developed entirely through field experimentation, without laboratory testing or engineering analysis. The cumulative effect of thousands of individual innovations created logistics capability that German intelligence consistently underestimated. Wehrmacht analysts, receiving reports of American vehicles crossing rivers at unexpected locations, attributed successes to favorable conditions rather than systematic capability. They couldn't accept that enemy forces possessed comprehensive water-crossing ability developed through improvisation rather than official programs. This systematic rejection of uncomfortable reality characterized German intelligence failures throughout the war. When evidence contradicted assumptions, analysts questioned evidence rather than revising assumptions. Reports of American vehicles fording deep rivers were dismissed as exaggerations. Accounts of supply operations continuing despite destroyed bridges were attributed to temporary bridging operations. The alternative that Americans had solved problems Germans considered unsolvable was psychologically unacceptable. By late April 1945, American logistics operated on fundamentally different principles than any previous military force. Supply lines functioned independently of road networks. Rivers represented minor delays rather than serious obstacles. Bridge destruction, which German doctrine considered decisive defensive action, achieved virtually nothing. American armies advanced as if infrastructure was irrelevant because, increasingly, it was. The contrast with German logistics was stark. Wehrmacht supply systems depended absolutely on functioning infrastructure. Destroyed bridges halted supply columns for days. River crossings required engineering operations. Supply routes followed roads because cross-country movement was impossible for standard vehicles. These limitations, which seemed normal within German operational framework, represented crippling disadvantages against enemies who had overcome them. Soviet forces, observing American waterproofing techniques, attempted similar modifications with limited success. Red Army mechanics lacked both the materials and the technical expertise for effective implementation. Soviet military culture, which emphasized centralized control even more strongly than German culture, provided no framework for individual initiative. Modifications required official authorization, which was seldom granted. The few Soviet units that implemented waterproofing did so using captured American vehicles rather than modifying their own equipment. This approach provided limited capability but demonstrated recognition of waterproofing's tactical value. Soviet commanders consistently requested American jeeps specifically because of their water-crossing capability, which Soviet vehicles couldn't replicate. British forces adopted American waterproofing techniques more successfully. British mechanics, working alongside American units, observed procedures and implemented similar modifications. By April 1945, significant British units possessed water-crossing capability approaching American standards. British military culture, which combined formal hierarchy with practical improvisation, accommodated innovation more readily than German rigidity. The technical comparison between American waterproofed jeeps and German specialized amphibious vehicles reveals instructive contrasts. Germany produced Schwimmwagen, purpose-built amphibious vehicles designed for water operations. These vehicles represented sophisticated engineering, with propeller drive systems, watertight hulls, and specialized components. Approximately 15,000 were manufactured throughout the war. American waterproofed jeeps, by contrast, were standard vehicles with field modifications costing approximately $50 in materials per vehicle. They couldn't match Schwimmwagen's water performance. They forded rivers rather than swimming across them. But American forces possessed hundreds of thousands of waterproofed jeeps versus Germany's thousands of specialized vehicles. Quantity and availability proved more valuable than technical superiority. The strategic lesson was clear. Adequate capability available universally defeats, superior capability available rarely. German forces possessed better amphibious vehicles, but insufficient numbers. American forces possessed cruder solutions but overwhelming abundance. In warfare, where logistics determined operational tempo, abundance trumped sophistication. The waterproofing program's cost-effectiveness highlighted another crucial advantage. Converting a standard Jeep to water-crossing capability required approximately 4 hours of mechanic time and $50 in materials. This investment enabled operational flexibility that no amount of planning could otherwise provide. The return on investment was extraordinary minimal expenditure producing strategic-level impact. German development of equivalent capability would have required months of testing, establishment of production facilities for specialized components, and complete retraining of mechanics. The organizational and financial investment would have been enormous. By the time German forces could have fielded comparable capability, the war would have ended. American improvisation achieved in weeks what German methodology would have required months or years to accomplish. The documentation gap between American and German approaches reveals cultural priorities. German engineers produced comprehensive technical manuals for their specialized vehicles. Every component was documented, every procedure was specified, every contingency was addressed. The documentation was exemplary by engineering standards. American waterproofing, by contrast, had virtually no formal documentation. Techniques spread through demonstration and practice. Mechanics learned by watching other mechanics. No official manuals existed until after war's end. Yet American forces achieved comprehensive capability, while German forces possessed excellent documentation for limited equipment. The comparison suggests that in rapidly evolving situations, knowledge transfer through personal networks surpasses knowledge transfer through formal documentation. Documentation requires time to produce and distribute. Personal demonstration transfers knowledge immediately. The waterproofing program's success depended fundamentally on trust. Commanders trusted sergeants to modify vehicles appropriately. Sergeants trusted mechanics to implement modifications correctly. Mechanics trusted their own judgment to solve problems as they arose. This distributed trust enabled rapid adaptation. German military culture, which concentrated trust in hierarchy and documentation, couldn't replicate this flexibility. When American commanders authorized waterproofing without official approval, they accepted personal responsibility for results. If modifications failed catastrophically, commanders faced potential court-martial. This risk-taking characterized American military leadership in ways German leadership avoided. German officers, operating within strict procedural frameworks, rarely accepted personal responsibility for unauthorized actions. The difference produced contrasting organizational behaviors. American units that experimented with waterproofing risked failure but achieved capability advantage. German units that awaited official authorization avoided risk but forfeited opportunity. In aggregate across thousands of decisions, American risk-taking produced cumulative advantages that German risk avoidance couldn't match. By war's end, American waterproofed vehicles had crossed thousands of rivers at tens of thousands of locations. The capability that began with Staff Sergeant Henderson's improvisation had become fundamental to American operational doctrine. Post-war technical manuals incorporated waterproofing procedures as standard maintenance tasks. What started as unauthorized field modification became official military practice. The institutional learning demonstrated American military's capacity to recognize effective innovation and institutionalize it rapidly. Techniques that proved valuable in combat were codified into doctrine quickly. German military, by contrast, struggled to incorporate field innovations into official practice. Innovations that contradicted established doctrine were often rejected regardless of battlefield effectiveness. The waterproofing legacy extended into post-war military vehicle design. American military specifications for post-war vehicles included fording, capability as standard requirements. Vehicle designs incorporated lessons learned from wartime waterproofing. Air intake positioning, electrical system sealing, and drivetrain venting reflected practical experience gained through improvisation. German post-war vehicle development, conducted under Allied occupation, similarly incorporated waterproofing principles. But the knowledge came from studying American techniques rather than indigenous innovation. The irony was profound. Germany, which possessed superior automotive engineering tradition, learned river-crossing capability from American mechanics using crude field modifications. The technical evolution from Henderson's initial canvas covers to comprehensive waterproofing protocols, demonstrated how practical experience generates sophisticated understanding. No amount of theoretical engineering could have anticipated every challenge that actual river crossings revealed. Only through repeated practice, failure analysis, and iterative refinement did comprehensive methodology emerge. This pattern practical experience generating knowledge that theory cannot predict represents fundamental truth about innovation. Theoretical analysis identifies possibilities. Practical implementation reveals realities. Organizations that embrace experimentation learn faster than organizations that demand theoretical certainty before action. American forces that waterproofed vehicles and learned through practice surpassed German forces that awaited theoretical validation before attempting modifications. The final assessment of waterproofing's impact must acknowledge its limitations. Waterproofed jeeps couldn't cross all rivers under all conditions. Deep, fast-flowing rivers remained impassable. Vehicles occasionally failed despite proper waterproofing. The capability was not absolute, but it was sufficient. Sufficient capability available broadly proved more valuable than absolute capability available narrowly. This principle that sufficiency distributed widely defeats perfection, concentrated narrowly determined warfare's outcome as decisively as any battle.